All right, so we are sharing screens. We're good to go. Deanna, thank you for the lovely introduction. Thank you for my committee for all of the guidance and for being here today. And let's get started. So throughout this dissertation, I thought a lot about the nature of sensation, especially if that sensation is coming from a hand. Anatomical hands give a wide variety of sensation, from the position of the fingertips to the pressure one might feel when trying to hold and crack an egg. Now, this is possible through an incredible combination of motor commands, sensory receptors in your muscles and skin, and a lot of processing in the brain that creates a mental model of your body and what you might be interacting with. But individuals with upper limb amputation lose access to a lot of this information, along with the loss of their hand. Most common approaches for addressing limb loss is the prosthetic limb. However, these are typically designed for grasping and actuation more than sensation. The two main types of active upper limb prostheses are myoelectric and body-powered devices. Now, a body-powered device has been around for a long time. It's driven by cable actuation, so an individual is wearing a harness, and they use the motion of their scapula to put tension on a cable that then opens or closes, typically a hook at the end of the prosthesis. And what's neat about these devices is that that movement at the end of the device is coupled directly to the motion of the individual's body, which gives them a sense that experts call extended physiological proprioception. Individuals with a prosthesis also receive feedback through incidental means. So when their prosthesis comes into contact with the environment, it makes sounds. They can see when they've grabbed an object, and a lot of them depend on that visual feedback. And they can feel the force of lifting objects and coming into contact with things via the socket, which is that interface between them and the device. Myoelectric prostheses are actuated by using signals that we collect from the residual muscle of an individual. So when an individual flexes or extends their muscles in their residual limb, electrodes on the surface of their skin that are pressed against it in that prosthetic socket pick up on these signals and give a velocity command to the prosthetic hand, typically. Now, these velocity commands aren't how we control our anatomical limbs. We're not tracking how fast or slow our hand is opening and closing. And so there's a little bit of a disconnect for myoelectric devices between the control signals that they're putting out and where their hand actually is in space. They're not sort of getting that closed loop unless, again, they are looking at the device. Maybe they're listening for the motors whirring in their hand, but there's definitely a lack of sensation there. Now, the loss of sensory feedback can definitely negatively impact the already reduced levels of function and control an individual has with their device. And in turn, these functional deficits can lead to device dissatisfaction, disillusionment, and ultimately abandonment. By one estimate, up to 26% of upper limb prosthesis users end up abandoning their device, with a lack of function and sensation being major motivators. However, it's difficult to determine how best to improve sensation, because empirical data on sensation, especially in these commercially available devices that people are actively using, is almost non-existent. A recent literature review of comparisons between body-powered and myoelectric prostheses only found a single study that mentioned sensation, and that data was all expert reviews and opinions, not empirical data. So what's more, while many studies in the field that do sort of investigate sensation, how can we deliver more sensation to individuals, these studies are often difficult to generalize because many of them either involve individuals with intact limbs using a prosthetic emulator or bypass. So these are people that obviously are not using prostheses in their day-to-day life, or they're giving custom devices to individuals with amputation. So again, not wholly generalizable because these individuals don't have experience with those devices. So briefly, I addressed this specific gap in how can we empirically measure sensation in commercially available devices in the first aim of my dissertation by developing a protocol for directly comparing the availability of this sort of incidental feedback, these portions of sensory information that the individuals are getting to individuals using anatomical limbs and individuals using body-powered and myoelectric prostheses. This work was published in TNSRE, and it was the first study to actually directly compare myoelectric and body-powered users using their own devices. We found that individuals with body-powered devices did have a little bit more feedback through that cable-actuated system. They could get force feedback from the tasks that we were asking them to do, specifically when they were asked to determine the stiffness of different objects that we were presenting to them. And we found that the importance of sensory feedback was dependent on tasks. So when we're asking them to estimate object size, where it's a very discrete sort of impact when they make contact with a device, individuals with myoelectric devices could use that information, but they couldn't determine the more sort of continuous force feedback for determining stiffness. So this work motivated me to think, all right, if commercially available devices aren't quite sufficient, where is the field headed next? So one method for delivering additional sensation to an individual, additional information, is through sensory substitution. Using this method, one sensation by sensors in the prosthesis, for example, pressure sensors in the prosthetic fingertips, can be communicated to the user via another mode of sensation, in this case, vibration. So you grab something and a little vibrotactor vibrates on the surface of your skin. Sensory substitution can give individuals greater ability to control the position of their prosthesis, modulate its grasping force, and determine object properties like size or stiffness. We can also leverage existing neural pathways to give individuals with amputation sensation that's actually aligned with their brain, with their mental map of how they experience sensation before their amputation. So here we can see one branch of the median nerve. This is carrying sensation away from sort of the base of the thumb here. And post-amputation, the thumb isn't there anymore, but those nerves still are. The routing from the thumb up to the brain still exists. It's just amputated and we don't sort of have access to it anymore. It's not going to the place that the brain expects it to go. So if we stimulate this free nerve ending proximal to that amputation site, then the brain can interpret this as sensation coming from a thumb that is no longer there in what we call the phantom hand. So it's possible to stimulate these nerves in a variety of ways. You can stimulate them from the surface using powerful electrodes, or by surgically implanting different technologies into the skin and around the nerves. And we'll get into all of that a little bit more later. So in this, all right, so we have these novel technologies that we can use to stimulate individuals. How does this actually look in this sort of feedback loop? So individuals are still, individuals are still having some intent for how they want to move their phantom hand, and we can pick up these signals from those peripheral nerve interfaces. We can pass those through machine learning algorithms and classifiers in order to build prosthetic commands that then command that neuroprosthesis to move. And then we can take advantage of sensors on that device to encode stimulation that tells an individual information about what they are interacting with. Those nerves, now that they're stimulated, are sending messages up through those pre-existing pathways to the brain, and then the user is interpreting that information in some way. But sensors and stimulation are not common in commercially available devices. And part of this reason may be that there are a lot of decisions that we need to make and a lot that we need to learn in order to make these processes effective long-term. So one question is, what nerves do we stimulate? So for the hand, the ulnar and median nerves innervate the palmar side of the hand, and these are very useful, but is one more sensitive or useful than the other? What technologies do we use? So each of these technologies has various pros and cons. Is there one that's better for certain participants or populations? How do we actually generate that sensation? So before I said that, okay, we stimulate a nerve, what does that mean? Most individuals, most studies use these square waves, and there are safety guidelines that exist to make sure that you don't hurt anyone with this stimulation, but not a lot of guidelines to actually determine what parameters to use. And then there's just questions of how do we describe sensation? How do we characterize what characteristics are important to capture, and how do we tell that it's actually helping the end user? So in this dissertation, I will dive into my second aim, which was looking at how the existing literature reports on sensation, how they characterize it, and how they look at functional outcomes. For aim 3, I'm looking at applying these characterization techniques to a specific peripheral nerve interface. And then finally, we want to see, hey, is this actually useful? So the objective of that second aim was to develop guidelines for how to choose appropriate stimulation parameters for a given technology, characterize stimulation percepts or sensations, and quantify the functional benefits of sensation. And like I said, I was interested in doing this already, but the literature wasn't giving me what I needed. There were some expert reviews, there were a lot of amazing individual papers, but no guidelines for how I could start this process. So I conducted a systematic literature review and basically wrote what I wanted to find out in the literature. I plugged a few search terms into 3 major research databases and came out with over 5,000 papers that it was now my job, along with some wonderful collaborators, to go through and comb through their titles, abstracts, and the full papers in order to determine what was relevant for our paper. I used a lot of inclusion and exclusion criteria to determine this. So I was looking for studies that electrically stimulated individuals with limb loss, tossing out any opinions or expert reviews, non-human studies. There were a couple interesting ones in rats, and anything that didn't sufficiently report on their methodologies. And using this criteria, we whittled it down to 49 papers, which is still a lot, but less than 5,221. So through this review, we found 9 different technologies that individuals and different studies were using in order to give individuals with amputation this referred sensation to their phantom limb. And they varied widely in terms of invasiveness, with surface stimulation over on the left and intraneural stimulation, where they actually have electrodes piercing the nerve all the way on the right. And these also varied in terms of the number of channels that you had to stimulate different parts of the nerve, and in terms of the longevity of these different technologies. 40 of the papers in this review were looking at upper limb prostheses, and I also characterized how long each of these studies ran for. So this is very important, because if we're going to do a surgery for giving an individual sensation and improving their day-to-day life, we want to know that we won't have to go back in later. So only 3 technologies actually had studies that lasted over a year, and only a single one of those studies actually lasted up to just under or just over 3 years. And this is relevant because that means that the long-term viability of any of these solutions is difficult to assess. So, okay, on to the first question. How do we choose these stimulation parameters? So electrical stimulation for the purpose of evoking referred sensation is typically done in discrete electrical pulses. All reviewed studies utilize stimulation pulses with square waveforms, negative and positive phases, and phases with the same total charge, so the same area under that curve. We typically define these waveforms in terms of their amplitude, or the height of that wave in milliamps, the pulse width, or how long each of those segments is for, and the frequency, how often we are stimulating. Now, increases in amplitude and pulse width result in increases in the total charge per pulse, and increases in frequency result in an increased charge per second. And then we also wanted to know, okay, what are the results of playing around with these different parameters? So changes in amplitude and pulse width were typically associated with increases in intensity, whereas frequency had some relationship with the type of sensation that individuals were experiencing. For example, one study found that changing the frequency range for stimulation made individuals experience a tingling sensation in their hands, sort of like pins and needles when your foot falls asleep. And if they changed that frequency, it would shift to a very naturalistic pressure sensation. However, because all these studies were doing very different methodologies, no one's actually replicated a lot of those sorts of results. So the second question is, how is sensation typically characterized? I'll move through this relatively quick because it's the focus of my third aim, but typically we care about the area of sensation. So where are individuals feeling sensation? What are they feeling? Is it that tingling sensation? Is it pressure, vibration? And then some important characteristics that didn't show up in a lot of studies, but I still think are important to call out, are the threshold. So how much stimulation we actually need, how much amplitude or pulse width to actually induce some sensation in an individual, and sensitivity to changing those parameters. You know, if we up the stimulation by 50 milliamps, do they notice a change in intensity? Finally, I wanted to know, how are we actually measuring the benefits of this stimulation? It's not enough to just write an IRB and, you know, stimulate a couple individuals and report on some neat phenomenon. We actually need to know that it's helping people. So the main 2 categories were object identification, so asking people to determine different properties of objects, and clinical outcomes. So these are things that are used in clinics today to determine if individuals with commercially available devices are dexterous, how capable they are with their devices, and these were being used in these studies for people with and without sensation to see if they improved. Finally, a lot of studies had these custom sensory tasks. These were a little bit all over the place. A lot of people handling fruit, plucking stems off cherries, holding grapes. But really the main sort of through line for all of these is proving that these individuals can grasp objects without crushing them, that they have some sensitivity to that sensation that we are giving them through stimulation. And all of these studies found benefits in at least one task, with 4 showing mixed results due to a variety of features that, again, we'll get into a little bit later. So through this literature review, we found that, okay, there are several technologies that can provide referred sensation, but we don't have a lot of good control over where that sensation happens. We don't really know where someone's going to feel something until we stimulate. Stimulation methodologies were also similar in terms of the square waves, but parameters were changed based on the technology and what the study was trying to accomplish. And because of, like I talked about before, this heterogeneity in studies, they're all doing something different, they're all measuring things differently. It's actually really difficult to pull out these big trends from these papers. So one of the results of this literature review was also to propose a set of guidelines that future studies could use to standardize how we report sensation, what we measure, and how we talk about it, to hopefully improve the way that researchers can communicate and to move the field forward a little bit faster. And this work was published in the Journal of Neural Engineering and presented at a conference. So, okay, we have scoured the literature to find how people are characterizing sensation. Now I want to do it. So at the University of Michigan, we have, instead of, just sort of this generic peripheral nerve interface, we have what's called an RPNI. And the purpose of this aim was to use these metrics that we got from the literature review, characterize sensation in the RPNI, and then as a secondary objective, try to actually play around and try some different sort of exploratory measures with those RPNIs. So what does RPNI stand for? It stands for regenerative peripheral nerve interface. And RPNIs were developed here at the University of Michigan to treat neuroma pain in the residual limb, as well as to act as a method of prosthetic control. Now, the critical difference between RPNIs and the other methods that I reported on in my review is that rather than targeting nerves from the surface of the skin or directly stimulating a nerve, the RPNI is an artificial biological construct that's created using the nerve and might interact with it in new ways. So to construct an RPNI, a surgeon excises a sliver of muscle, typically from the quad, and then wraps that muscle around a free nerve ending in the amputated limb. Makes a little biological burrito. And the nerve naturally reinnervates and the RPNI revascularizes over the course of about 3 months. And then using an implanted electrode, we can record activation potentials, we can use this for prosthetic control, and we can deliver sensation. So for this work, I've worked with 4 individuals who each underwent transradial amputation prior to the study, and all participants had RPNIs constructed out of their median and their ulnar nerve, and then 1 participant had RPNIs constructed out of their dorsal radial sensory nerve as well. These participants were enrolled in the study for various lengths of time. Notably, my work reports on 3.5 years of P2, which is a fantastic data set. And then also notably, P4 is our most recent participant with only 5 months of data collected so far. I also want to note that some basic sensory characterization began prior to my involvement in the study as some regulatory measures, but I did conduct sensory experiments for most of P2 and then all of P3 and P4. So returning to, okay, these important characteristics that we got from the literature review, I wanted to characterize RPNI sensation in terms of percept location and quality, their functional stimulation range, so over what range can we stimulate to generate sensation, and how sensitive they are to changes in that stimulation. For each participant, for each collection, the participant was seated in a comfortable seat and was stimulated via wire ports on their upper arm. So these amazing volunteers actually have these all year long. When they leave the lab, we put a bandage around it, but they come in, we peel that off, and we plug right into them to wires that are running to their residual limb, or to their residual muscles and to the nerves in the RPNIs. Stimulation waveforms were all square, charge balanced biphasic waveforms like we saw in the literature review, and those were done through a digitimer box. And additionally, the pulse width and the frequency of these waveforms was typically fixed, and we were just experimentally modulating the amplitude. So the first element we want to characterize is that location of sensation. So, okay, we've got our sensory map. We expect median sensation to show up here. We stimulate an ulnar RPNI. We expect it to show up there. But we don't really know what's going to happen until we stimulate these RPNIs. What you're about to see are a bunch of hand maps. This legend shows dotted lines for verbal responses that these participants gave, which happened prior to me joining the study, and then solid lines and shaded regions for reports that they gave via a custom app that I designed for these data collections. So here we can see the ulnar RPNI sensation locations for all of our participants. You can see that they mostly align with where we expect. This sort of left side of the right hand. Sorry, that was weird. We have a couple notable deviations from this. So P3 had some sensation in the wrist, and P4, when we stimulated either of their RPNI, ulnar RPNIs, they actually felt sensation in their index finger. Going over to the median RPNIs, we again see that most of that sensation aligns with what we expect, with the exception of one of P3's median RPNIs. And then finally, the one radial RPNI for P4. Now, typically when we stimulate the radial nerve, we expect sensation along the back of the hand. That's what the radial nerve innervates. However, we did get, they did experience sensation sort of along the backside of their residual limb. And reasons for these discrepancies may be the age of the participant, previous medical history. We had one participant who had underwent some treatments prior, another participant who had gone through several surgeries prior to enrolling in our study. But answering these sorts of questions requires a much larger cohort. So next we're on to determining an individual's functional stimulation range. This is very important because we want to know how much stimulation we need for them to feel something, and then how high can we go before it becomes uncomfortable. So to determine perception thresholds, prior to me arriving and running sensory characterization, we would start at 0 milliamps. We would step up and ask the participant, did you feel anything or not? If the answer was no, indicated by a red circle, then that would continue until they said yes. And then we mark that with a blue circle, take the number down. I expanded on this methodology by introducing alternations around that threshold at smaller and smaller step sizes to establish what I hope is a more representative result. I also began characterizing discomfort thresholds with the participants. For discomfort thresholds, rather than asking, did you feel sensation? I asked, was that sensation uncomfortable? So for perception thresholds, we repeated this process approximately once a month. In this case, this is P2, so this was over the span of that 3.5 years. Discomfort thresholds were only plotted 3 times, the last 3 sections of this data set. The bars on the right then show us that functional stimulation range. So these bars are the range of amplitudes that we can stimulate an individual and expect them to feel sensation. The dots on the bottom show the average, and the bars show the standard error for those thresholds. And then the tops are associated with the discomfort thresholds. So on the left here are 3 data sets for P1 through 3. Well, there are some local trends. On the whole, we can see that the perception thresholds are pretty consistent over time. Additionally, the discomfort thresholds are more variable than the perception threshold, which we expect, because the question of was that uncomfortable has a little bit more variance and subjectivity to it than did you feel sensation or not. For completeness, I'll also share the data for P4. Only one of P4's RPNIs actually elicited sensation all 5 of those months. However, in the last 2 sessions, we got sensation for all 5 of those RPNIs. So this may just be indicative of those RPNIs sort of coming online, as P4 started sensory thresholding much sooner after the actual construction of their RPNIs compared to all of the other participants. So finally, the last piece that we want to do for this characterization is the sensitivity to changes in that stimulation. This is what we need to understand in order to give someone a sense of pressure so that they're not just getting sort of an on or off. So we pick an intensity between that perception and discomfort threshold. That's going to be our reference. We have a bunch of test intensities that are around that reference. And we do what's called a 2 alternative force choice protocol. So this is something that you might find, you might have all done in the optometrists. I present one intensity and ask, is this one higher? And then I present another intensity and ask, is that one higher? We do this a lot of times. There were 9 reference intensities. We did 10 blocks for each experiment, 2 different experiment days, and we did this for every single one of their RPNIs that had a stable perception and discomfort threshold. All of those individual answers are then data points, and what we're hoping for is that the higher the intensity from that reference, the more likely they are to say, yes, that one was higher. And the more accurate they are, the smaller their just noticeable difference and higher their intensity. So these are the results from that process. So I'll just highlight that is the just noticeable difference. So that's how many basically milliamp steps an individual can perceive with some confidence that like, okay, I detect a difference in intensity. But these numbers aren't super useful, even though this is typically how it's reported in the literature, because everyone has a different functional range. It doesn't matter if you can tell a difference in 0.25 milliamps if your whole range is 0.3 milliamps. So the metric that I prefer is the percent of range, which tells us how basically many of those just noticeable differences fit inside that wider functional range. And with this metric, we can say things like participants could receive at least 7 distinct levels of intensity across all of these RPNIs. So that's pretty good. If they're interacting with the world, they get 7 distinct levels of intensity. And this is less than intraneural. So one other study did report on levels of intensity for an intraneural stimulation method, which is actually an electrode piercing a nerve. And they saw closer to 20 levels of intensity, but they also have a more invasive process and one that hasn't been proven to actually be as, doesn't have the longevity of RPNIs. So all that characterization was important to do one RPNI at a time, one channel at a time, to limit variables, limit the time that we actually need for experimentation. So for P2, these are sort of the individual areas of sensation that she felt for 3 of her RPNIs. But that's not how our hands work. That's not how we expect future prostheses to work. We actually want someone to be able to get multiple experiences at the same time and synthesize that information the way that you would with an anatomical hand. So what happens when we stimulate RPNIs simultaneously? So for, again, P2, we stimulate the median RPNI, we get sensation here. Ulnar RPNI, we get sensation over here on the other side of the hand. And when we stimulate both, hey, we get sensation at both of those locations. Great. But one thing that was sort of interesting to me is that these 2 stimulation waveforms, these square waves, are in phase. What happens if we shift one just a little bit, make it out of phase? Well, now what we actually noticed is that that ulnar RPNI sensation over here on the side of the hand actually got masked. So the participant, we were using the same amplitudes, pulse widths, frequencies, just shifting those waveforms a little bit, and they were only perceiving the sensation from their median RPNI. Now, we didn't conduct a full experiment around this, but to my knowledge, no other study has reported on the effects of synchronicity in those waveforms for simultaneous stimulation. So I hope this investigation can be useful and interesting to explore in future studies. I also noticed another interesting phenomenon under certain conditions. So again, we have our ulnar sensation over here, our median sensation over there. But if we brought that amplitude down just to the perception threshold, then in certain cases, we could get 1 sensation rather than 2 in the center of the hand. Now, this is really interesting because I can't make that happen with any single RPNI. And if I vary the levels of intensity for the median and ulnar RPNIs just a little bit, I can actually make that sensation walk back and forth across the hand. This is pretty cool to me because no one else has reported anything like this either. And it opens up the possibility that we might be able to use less electrodes in order to achieve more areas of sensation. But it's not 100% reliable. I was able to accomplish this in 3 out of the 6 attempts that I made after first observing this phenomenon. So while it hasn't been reported in the literature yet, I hope that reporting that this is possible encourages other people to try it. So we've seen that RPNIs can elicit sensation in a predictable way in terms of the location and intensity of sensation, and that the stimulation amplitude necessary to evoke RPNI sensation is pretty consistent over time, which is awesome for a pitch for, hey, we can use these potentially in patients in the future. We also showed that participants are sensitive to changes in stimulation amplitude, and a subset of this data was published and presented at the International Conference on Rehabilitation Robotics in the Netherlands, and a full data set will be published soon. So, okay, we've scoured the field for how do we characterize and test sensation, and we've characterized sensation in our regenerative peripheral nerve interface. Now we want to actually put it to work. We want to see, can these RPNI sensations be useful in a functional task? So again, I took a look at the results from the literature review. So we had 21 studies that did bidirectional testing, and we had 4 that showed these mixed results. And one in particular stood out because this study was actually taking a physical prosthesis. So it had sensors that they couldn't move the location of those sensors. They couldn't change what information an individual had access to, and was forcing the sort of stimulation parameters of their participants, which we talked about. We can't control where they feel this sensation. We can't control what they feel right now, and asking them to sort of change and re-perceive their phantom sensations to the sensors on the prosthesis. That particular participant performed worse than the participant who, hey, their phantom sensations naturally lined up with the sensors on the device. And this seems like a common issue in sort of neural prostheses. So one method to get around this and rapidly prototype prosthetic solutions for individuals is by using virtual reality. Virtual reality is fully modular, so I can put sensors wherever I want. I can change the configuration of a prosthesis to make it larger, shorter, longer, change the number of motors that an individual has access to. And VR has been proposed as a way to design and train new prosthesis users because it's relatively low cost and because it can be gamified. People really like to have this gamification that encourages them to practice and to complete different protocols. To prove the efficacy of VR as a design and training solution, several groups have recreated clinical tasks in the physical space and then created those tasks in the virtual space as well, and seen how the results of the physical and virtual tasks actually compare. And in one study that looked at participants post-stroke, they found actually a high correlation. Participants who did well in physical box and blocks, which is a task that requires individuals to grab blocks and move them from one side of the partition to the other. Participants who scored high in the physical version also scored high in the virtual version and did so consistently. So building a virtual environment is pretty complex. We didn't have this full system just sort of laying around, and it requires several components to act in concert. These include visualization, motor control, sensory feedback, and a physics engine so that individuals aren't just playing a game. They really need to apply effort to grab and hold these blocks as they're moving them. Well, the technical aspect of visualization, popping on a VR headset and putting someone in a virtual space, is relatively easy because of the popularization of VR gaming. We wanted this experimental area to be welcoming, not just sort of a blank space, an empty void, and no textures. So over time, I developed and improved the space in order to make a sort of clinic setup in a low poly park within the Unity game engine that would be welcoming to our participants that had never interacted with virtual reality, hadn't really played video games before, and weren't really familiar with what they were going to see when they put the headset on. It was also important to scale the virtual environment to match our physical lab setup so that the participants' movements were one-to-one and intuitive in the virtual space. For the control portion, I leaned heavily on previous work and support from students in Dr. Chestek's lab, who had already developed a protocol for training a Kalman filter to decode participant intent based on either these indwelling RPNI signals or surface electrode signals. I adapted this system and I sent the outputs of these decoding algorithms to the VR computer in order to take those in and push those out to the Unity visualization of the virtual hand. So this participant this is an early stage in experimentation. So the controller is just sort of strapped to their prosthetic socket, but they are using RPNI signals hooked up through our computer system and then passed over to the virtual space to open and close the hand and move around some virtual blocks. Now, while sensation did take several months to actually develop and get working in the virtual space as well, I'll skip over most of that part because it's pretty straightforward in terms of explaining the execution. Essentially, we have virtual hands in the virtual space that the user is moving around with this motion tracked controller. And we have areas of their phantom limb that we already know from the previous aim where we're expecting to get sensation when we stimulate different RPNIs. Now we just need to put virtual sensors, again, because this VR space is fully modular, on the places that match with those perceived areas of sensation. And when they touch something in the virtual space, we stimulate the appropriate RPNI and they feel sensation in that phantom hand. These participants then saw something akin to this, which is that virtual hand with highlighted areas that correspond to those virtual sensors and where they expected sensation. Finally, I needed to integrate a physics engine into the simulation so that participants were actually required to grasp objects and maintain that grasp. So I used Majoko, which is a platform that is useful for robotic applications for physics simulation, but has also been used in the prosthetic space, and had a way to integrate with the Unity visualization. Majoko allowed us to do object interactions between the virtual hand and the prosthesis. It had compliant joints so that the prosthesis wasn't just this rigid body that would instantly stop if it hit objects. And that video there is just an example of how the motion tracker was attached to the virtual space, so that the virtual hand could abide by all the physics laws and then try to snap to wherever the participant was trying to move their residual limb. So this is just a quick rundown of all of those systems talking to each other. We have Unity that is actually taking in camera system information to get the position and orientation of the controller and the headset. It's then rendering the appropriate graphics for the individual through their VR headset. We're taking surface electrode signals from the individual and collecting those and decoding them through a secondary PC, and then passing that information into our simulation through a custom Python script that was handing information between MATLAB and Unity. And then finally, the collisions that were calculated with Majoko were then sent to that Python script and published to the Nomad, which is what actually builds and sends the stimulation waveforms that generate the sensation. For the main task, participants completed a virtual version of the box and blocks task within the virtual environment. Participants had 1 minute to move as many blocks as possible from one side of the partition to the other. And they completed this task under several feedback conditions. So one was just using the visual feedback that they were getting through the headset. Another one had sensors on the virtual fingertips relay vibrotactile feedback to a controller that was mounted on their forearm. And then we engaged with the RPNIs. So in one setup, we had these sensors on the fingertips, which is how you're going to mostly be engaging with these blocks. And we referred those to the most appropriate RPNIs. So we have this sort of mismatch in the style of sensation and the somatotopy, or the location matching of the sensors and the perceived sensation. And then somatotopic sensation. So this, we just put sensors where the individuals already expected to feel that sensation. We also had participants attempt a rhythmic task that sort of attempted to see how quickly they could incorporate feedback into their control loop. So individuals had to juggle a ball and try to maintain it into a target area. Unfortunately, because we were using surface electrodes that required a lot of effort for flexion and extension from our participants, and they had to do this action frequently and quickly, they fatigued a little bit too quickly, and we weren't able to finish collections with these participants. So back to the experimental setup for the virtual box and blocks. The participant was set up with a Vive controller for motion tracking, one for vibrotactile feedback. Notice I'm not taping it to them anymore. Surface electrodes for measuring the muscle activity, and those RPNI electrode connectors for delivering them sensation. So now I'm just going to show a quick excerpt of one of the last sessions for P4. So in this trial, P4 was receiving location matched sensation to his RPNIs. So anytime he touched something with his virtual index finger, he was feeling it in the index finger of his phantom limb. And you can see he's really quickly able to grab a block, move it, release it, and he knows when that's happening because he's getting sensation, and that sensation is exactly where he expects it to be. Now in this plot, we have blocks moved on the y-axis within that 1 minute. And we can see that compared to, so we have white dots for no feedback and these green dots for this somatotopic RPNI-enabled feedback. And we can see that P4 did improve their performance from the no feedback condition. He actually performed similarly to a control participant who was just using their anatomical limb and a game controller. So they had complete control over the opening and closing of the prosthesis, and they both performed similarly. Now, interestingly, P2 did not show as much of an improvement in their scores, although notably P2 was also moving much slower and attempted to move half as many blocks compared to P4. So this discrepancy may be due to the fact that we were using these surface electrodes because our current setup didn't allow for simultaneous RPNI control and sensation, and P2 uses a body-powered prosthesis at home, whereas P4 uses a myoelectric prosthesis at home. So he was much more used to the ability to actually actuate and flex and extend in order to control that virtual hand compared to P2. So possibly if we improve her control, we might see a little bit more delineation in the results of this task. But in this study, I found that RPNI-enabled feedback didn't just have functional benefits to these participants, especially to P4. It had some qualitative ones as well. So bear with me, it's a little over a minute, but here's a testimonial for P4 right after this data collection that I think really sums up how special this project is. What are some things that stand out about trying to both control things in VR and also get the sensation?
When I was hooked up to RPNI, when I was moving the blocks, my hand stayed about in this position.
Your phantom hand?
The phantom hand. So when I was doing this, I was still opening and closing my phantom hand, but like right now it's kind of closed up like this, and it always wants to go, and I always have to struggle through the cement and open it up.
Yeah.
But during that, I was doing this, and it always opened and closed and kind of stayed in this position.
Okay.
And that helped me as I got faster in the blocks.
Sure.
My hand was only doing this.
Got it.
And
is that a new experience
yeah,
for you?
Yeah, that's this whole time I didn't get a cramp.
Wow.
So when I was doing that, now right now my hand is lock solid.
Sure.
Like this.
Yeah.
And my pinky's kind of free floating right now, but these are like this, and for me to open it, I'm really stressing this out right here.
It takes energy, it takes time.
Yeah, it's just not popping open, but while I was doing it, it felt pretty normal. And I think that's
very cool.
That's a new sensation.
Yeah. So I just want to hang on that for a second, but while I was doing it, it felt pretty normal. So in this investigation, I demonstrated that we could use a virtual reality environment to give participants referred feedback that corresponded to appropriate sensors on a virtual prosthesis. And that bidirectional control given in this way was both engaging and functional for our participants. What's more, I was actually able to alter P4's perception of his phantom limb by closing that internal control loop with a bidirectional control task. Now, the VR system definitely has some room for improvement, and I do intend to improve it so that we can make this an open source tool for other labs and groups to use. So to echo my first slide, I've spent a lot of my dissertation thinking about sensation, especially sensation in some sort of hand. We started talking about the suite of sensation in anatomical hands, but we've seen a lot of ways that prosthetic limbs can provide sensation too. Through both my initial investigation into commercially available devices and through my literature review, I found that sensation is difficult to measure and that the field has yet to come to a consensus on how to do so. However, it seems like building device-agnostic tools that allow participants to engage with them as individuals and bring their own experience to these collections, we might be able to more accurately assess sensation in them. I've also demonstrated that RPNIs are an effective addition to the methods we can use to interface with pre-existing neural pathways and generate referred sensation. But like other methods, RPNIs are limited, and there's a lot to learn before we can dictate aspects of sensation like location and quality. So in this dissertation, I have developed an experiment that can evaluate the function of individuals using their own devices. I've conducted a literature review to provide guidance for future work in delivering referred sensation. I've characterized that sensation in a peripheral nerve interface that we use here and developed here at the University of Michigan, the RPNI. And I've shown that we can use that RPNI as part of that bidirectional control loop to potentially improve sensation for these participants and hopefully prove that we can do this over long periods of time. So I have a whole lot of people to thank, and I can't thank them all. I will start by saying, Deanna, thank you for being the absolute greatest mentor. Any work that goes through you turns out the best that it can possibly be. And I'm so happy that you said yes when I came for visit weekend. But thanks to all of the other mentors and collaborators. Thank you to an incredible support network that I have through my family and my friends. I love all of you so much. Thank you if you've ever been on a Zoom call with me, for my rambunctious cat, who did give me a fresh scratch this morning. But during the pandemic, when I couldn't see people, it was real nice to not be alone in the apartment. And of course, to an incredible robotics community. I mean, thank you for letting me present on this stage and for being such a wonderful place to grow up and learn. I got to see this turn in from an institute to a department, and that is incredible. And of course, thank you to all my participants. I couldn't do any of this. I couldn't contribute to the literature without you. And thanks you for listening. All right.